Welcome F5 students. Today we are going to discuss about some examples on first shifting property or translation property. Some examples. Example, find Laplace inverse of es upon es plus 1 raised to 5. Second, Laplace inverse of es upon es plus 1 raised to 5 by 2. Solution. First, Laplace inverse of es upon es plus 1 raised to 5. Using first translation property of inverse Laplace transform. In the denominator here s plus 1, therefore we add this s plus 1 in the numerator. S plus 1, add 1 and subtract 1 here. S plus 1 minus 1. We get again es here. Es plus 1 raised to 5. By linearity property, Laplace inverse s plus 1 upon es plus 1 raised to 5 minus Laplace inverse of 1 upon s plus 1 raised to 5 is equal to Laplace inverse of, here s plus 1 get cancelled here, 1 upon s plus 1 raised to 4 minus Laplace inverse 1 upon s plus 1 raised to 5 is equal to, using first translation property of inverse Laplace transform, e raised to minus t Laplace inverse of 1 upon es raised to 4 minus, using first translation property here, e raised to minus t Laplace inverse of 1 upon es raised to 5 is equal to e raised to minus t Laplace inverse of 1 upon es raised to 3 plus 1 minus e raised to minus t Laplace inverse of 1 upon s raised to 4 plus 1 is equal to e raised to minus t. Laplace, we know that Laplace inverse of 1 upon s raised to n plus 1 is equal to t raised to n upon en factorial. Here and here 3, t cube by 3 factorial minus e raised to minus t raised to 4 by 4 factorial is equal to e raised to minus t raised to 3 upon 3 factorial, that is 3 into 2 into 1, that is 6, minus e raised to minus t raised to 4 upon 4 factorial, that is 4 into 3 into 2 into 1. Here 24. Laplace inverse of s upon s plus 1 raised to 5. We get equal to e raised to minus t cube by 6 minus e raised to minus t raised to 4 by 24. Next example. Second, Laplace inverse of s upon s plus 1 5 by 2 is equal to, here in the denominator s plus 1, we add this s plus 1 in the numerator, that is add 1 and subtract 1. Laplace inverse of s plus 1 minus 1 upon s plus 1 raised to 5 by 2 is equal to Laplace inverse s plus 1 upon s plus 1 raised to 5 by 2 minus Laplace inverse 1 upon s plus 1 raised to 5 by 2 is equal to Laplace inverse of, we put this in the numerator, s plus 1 raised to 5 by 2 minus 1, that is 1 upon s plus 1 raised to 3 by 2 minus Laplace inverse 1 upon s plus 1 raised to 5 by 2. Using first translation property of inverse Laplace transform is equal to e raised to minus t Laplace inverse 1 upon s raised to 3 by 2 minus Laplace inverse e raised to minus t Laplace inverse 1 upon s raised to 5 by 2 is equal to e raised to minus t Laplace inverse 1 upon s raised to 1 half plus 1 minus e raised to minus t Laplace inverse of 1 upon s raised to 3 by 2 plus 1. For this, Laplace inverse of 1 upon s raised to n plus 1 is equal to t raised to n upon gamma n plus 1. Here fraction, therefore we use gamma. is equal to also t raised to n upon n into gamma n is equal to e raised to minus t raised to 1 half upon gamma 1 half plus 1 minus e raised to minus t raised to 3 by 2 upon gamma 3 by 2 plus 1 is equal to e raised to minus t raised to 1 half gamma n plus 1, that is n into gamma n. Therefore 1 half into gamma 1 half minus e raised to minus t raised to 3 by 2 upon 3 by 2 gamma 3 by 2 is equal to e raised to minus t raised to 1 half upon here 2 gamma pi gamma 1 half, that is root of y minus e raised to minus t raised to 3 by 2 upon 3 by 2. Here gamma 3 by 2 means 1 half plus 1. Therefore 1 half into gamma 1 half is equal to twice e raised to minus t raised to 1 half upon root pi minus e raised to minus t. Here 2 into 2 4 e raised to minus t raised to 3 by 2 upon 3 into root pi. Therefore 2 e raised to minus t raised to 1 half root of pi minus 4 e raised to minus t raised to 3 by 2 upon 3 root pi. Next, evaluate Laplace inverse of s minus 14 upon s square minus 4s plus 8. Second, Laplace inverse of 8s plus 20 upon s square minus 12s plus 32. Solution. Laplace inverse of three s minus 14 upon s square minus 4s plus 8 is equal to Laplace inverse 3s minus 14 upon, for the perfect square, here a square minus 4s, but here plus 8, that is 4 plus 4. A square minus 4s plus 4 plus 4 is equal to Laplace inverse of 3s minus 14 upon a square s minus 2 bracket square plus 4. For the first translation property, in the denominator here s minus 2, therefore add this s minus 2 into the numerator, in which we get again 3s minus 14. Laplace inverse 3 into s minus 2 here 3s minus 6, but here minus 14, therefore add this minus 8 here. 3 into 2 minus 6 minus 8 is minus 14. S minus 2 bracket square plus 2 square. By linearity property separating, 3 times s minus 2 upon s minus 2 bracket square plus 2 square minus 8 times Laplace inverse of 3 into s minus 2, 1 upon s minus 2 bracket square plus 2 square is equal to 3 times using first translation property. E raised to minus 2t Laplace inverse of s upon a square plus 2 square minus 8 using first translation property. E raised to minus 2t Laplace inverse of 1 upon s minus 2 bracket square plus 2 square. That a square only. A square plus 2 square is equal to 3 e raised to minus 2t Laplace inverse of s upon a square plus 2 square. We know that Laplace inverse of s upon a square plus k square is equal to cos kt. Laplace inverse of 1 upon a square plus k square sin kt. Therefore here cos 2t Laplace inverse of s upon a square plus 2 square minus 8 e raised to minus 2t Laplace inverse of 1 upon a square plus 2 square, that is sin 2t. Next example. Laplace inverse of second 8s plus 20 upon a square minus 12s plus 32 is equal to. Laplace inverse of 8s plus 20 upon, for in the denominator we want perfect square. Therefore here a square minus 12s, here 2 into 6, therefore here 36. If we add 4 then subtract 4 is equal to Laplace inverse of 8s plus 20 upon s minus 6 bracket square minus 2 square. Using linearity property of inverse Laplace transform, 8 times adjust here s minus 6, adjust s minus 6 in the numerator. Therefore 8 s minus 6 adjust minus 6 in the numerator, in which we get again 8s plus 20. Therefore 8 6 are 48 minus 48, but we want 20 here. Therefore write here 68. S minus 6 bracket square minus 2 square is equal to using linearity property at Laplace inverse s minus 6 upon s minus 6 bracket square minus 2 square plus 68 Laplace inverse of 1 upon s minus 6 bracket square minus 2 square. Using first translation property, 8 e raised to minus 60 plus 60. E raised to 60 Laplace inverse of s upon s minus 6 s square minus 2 square plus 68 e raised to 60 Laplace inverse of 1 upon a square minus 2 square is equal to 8 times e raised to 60. We know that Laplace inverse of es upon a square minus 2 square, that is cos h2t, and Laplace inverse of 1 upon a square is kt, a square minus k square sin hkt. We get cos 2t h2t, that is hyperbolic function 68 sin h 2t. In the example, second translation or shifting property of shifting property. If Laplace inverse of Fs is equal to Ft, then Laplace inverse of e raised to minus ks Fs is equal to gt function of t is equal to, in curly bracket, f of t minus k if t greater than k, 0 if t is less than k. We have Fs is equal to, by definition of Laplace transform, Laplace of Ft is equal to Fs e raised to minus est Ft dt is equal to multiplying both sides by e raised to minus ks Fs e raised to minus ks 0 to infinity e raised to minus est Ft dt is equal to, here e raised to minus ks is constant with respect to t, therefore enter in the integration 0 to infinity e raised to minus as e raised to minus st Ft dt is equal to 0 to infinity e raised to minus s is common k plus t into s Ft dt. Put p plus k plus t is equal to u, suppose, implies p differentiate this with respect to, differentiate this, derivative of constant is 0, derivative of t is dt is equal to derivative of u is du. After substitution, the limits are also changes. Limits of t and limits of u. If t is 0, therefore k plus 0 is equal to u, therefore u is equal to k. If t is infinity, then u also infinity. Therefore we get k to infinity e raised to minus us here t, therefore f of u minus k du. Here u k plus t is equal to u, therefore t is equal to u minus k is equal to, from 0 to infinity, from 0 to k, e raised to minus us, we take here 0 du plus k to infinity, e raised to minus us f of u minus k du. Therefore, what is this? That is 0 to infinity, e raised to minus est gt dt. By definition of Laplace transform, this is Laplace of gt, e raised to minus ks into fs. Therefore, Laplace inverse of e raised to minus ks fs is equal to gt. What is gt? F of t minus k if t is greater than k, and 0 if t is less than k. Okay, we stop here.